If you've ever wondered how microscopic particles can explain macroscopic properties like temperature and pressure, you're in the right place. Statistical mechanics, sometimes called statistical physics or statistical thermodynamics, is a mathematical framework that uses statistical methods and probability theory to understand large groups of microscopic entities. It's a bit like trying to predict the behavior of a crowd by understanding the actions of individual people. This field isn't just limited to physics, it has applications in biology, chemistry, neuroscience, computer science, information theory, and even sociology. So what's the main goal of statistical mechanics? Essentially, it aims to explain the properties of matter in bulk, based on the physical laws that govern atomic motion. Think about it. How does the random motion of countless atoms and molecules result in stable properties like temperature and pressure? That's where statistical mechanics comes in. It all started with classical thermodynamics, which deals with macroscopic properties such as temperature, pressure, and heat capacity. Classical thermodynamics can describe these properties but doesn't explain them in terms of the microscopic particles involved. Statistical mechanics bridges this gap by using the idea that these properties result from the collective behavior of vast numbers of particles, each with its own set of microscopic parameters that fluctuate around average values and are characterized by probability distributions. Now, classical thermodynamics is primarily concerned with systems in thermodynamic equilibrium. But what happens when a system is out of equilibrium? That's where non-equilibrium statistical mechanics comes into play. This branch studies how systems evolve over time when they're not in equilibrium. It applies to processes like chemical reactions and the flow of particles and heat. One of the key concepts here is the fluctuation-dissipation theorem, which helps us understand how small fluctuations can lead to large-scale changes in a system. For example, think about a chemical reaction. At the microscopic level, molecules are constantly colliding and reacting in seemingly random ways. But when you look at the reaction as a whole, it follows predictable patterns governed by statistical laws. Statistical mechanics doesn't just stop there. Let's explore the principles of mechanics and ensembles. In physics, two types of mechanics are usually examined: classical mechanics and quantum mechanics. For both types of mechanics, the standard mathematical approach is to consider two main concepts. First, we have the complete state of the mechanical system at a given time. In classical mechanics, this is mathematically encoded as a phase point. In quantum mechanics, it's represented as a pure quantum state vector. Second, there's an equation of motion that carries the state forward in time. For classical mechanics, this is Hamilton's equations, and for quantum mechanics, it's the Schrödinger equation. Using these two concepts, we can calculate the state at any other time, past or future, in principle. However, there's a disconnect between these laws and our everyday life experiences. We don't need, nor is it even theoretically possible, to know the exact microscopic positions and velocities of each molecule while performing processes at the human scale, like a chemical reaction. This is where statistical mechanics comes in. It bridges the gap between the laws of mechanics and our practical experience of incomplete knowledge by introducing some uncertainty about which state the system is in. Ordinary mechanics considers the behavior of a single state, while statistical mechanics introduces the statistical ensemble, a large collection of virtual, independent copies of the system in various states. In classical statistical mechanics, the ensemble is a probability distribution over phase points, usually represented in phase space with canonical coordinate axes. In quantum statistical mechanics, the ensemble is a probability distribution over pure states, summarized as a density matrix. These ensembles can be interpreted in different ways. They can represent the various possible states that a single system could be in, known as epistemic probability, or the states of systems in repeated experiments, known as empirical probability. Both interpretations are often used interchangeably. Each state in the ensemble evolves over time according to the equation of motion. Thus, the ensemble itself, or the probability distribution over states, also evolves. This evolution is described by the Liouville equation in classical mechanics and the von Neumann equation in quantum mechanics. One special class of ensembles is those that do not evolve over time, known as equilibrium ensembles. Statistical equilibrium occurs when, for each state in the ensemble, The ensemble also contains all of its future and past states with equal probabilities. This is different from mechanical equilibrium, which is a state with a balance of forces that has ceased to evolve. The study of equilibrium ensembles of isolated systems is the focus of statistical thermodynamics. On the other hand, non-equilibrium statistical mechanics addresses the more general case of ensembles that change over time, or those of non-isolated systems. Now that we've explored the principles of mechanics and ensembles, it's time to dive into the three fundamental thermodynamic ensembles often discussed in statistical thermodynamics. These ensembles provide a bridge between microscopic states and macroscopic thermodynamic properties. First, we have the microcanonical ensemble. This ensemble describes a system with a precisely defined energy and a fixed number of particles. Each possible state of the system that meets these criteria is equally probable. Next, let's talk about the canonical ensemble. Here, the system has a fixed number of particles but can exchange energy with an external heat bath at a precise temperature. The states within this ensemble have varying energies but the same composition, with different probabilities assigned based on their total energy. Lastly, we have the grand canonical ensemble. This ensemble describes a system that can exchange both energy and particles with a thermodynamic reservoir. The reservoir has a precise temperature and specific chemical potentials for various particle types. The states in this ensemble vary in both energy and particle number, with probabilities depending on their total energy and total particle numbers. Now, let's take a closer look at quantum statistical mechanics and its unique characteristics. Quantum statistical mechanics is statistical mechanics applied to quantum mechanical systems. In quantum mechanics, a statistical ensemble or probability distribution over possible quantum states is described by a density operator. This density operator is a non-negative, self-adjoint trace class operator with a trace of 1 on the Hilbert space that describes the quantum system. The density operator encapsulates all the statistical properties of a quantum system. This includes mixtures of pure states, which can represent various possible states the system might be in. Unlike classical probabilities, which are straightforward, quantum probabilities can interfere with one another, leading to phenomena like superposition and entanglement. This can be shown under various mathematical formalisms for quantum mechanics. One such formalism is provided by quantum logic. Quantum logic redefines the principles of classical logic to accommodate the peculiarities of quantum phenomena. For instance, in quantum logic, the proposition A and B might not hold the same truth value as in classical logic due to the non-commutative nature of quantum operators. Understanding the density operator and its evolution over time is crucial for predicting the behavior of quantum systems. The evolution of the density operator in time is governed by the von Neumann equation, which is the quantum analog of the Liouville equation in classical mechanics. This equation ensures that the probabilities remain consistent with the principles of quantum mechanics over time. Let's dive into the fascinating applications of statistical mechanics. The ensemble formalism can be used to analyze general mechanical systems where there's uncertainty about the state of a system. This approach isn't just theoretical. It has practical applications across various fields. For example, ensembles are used in the propagation of uncertainty over time, regression analysis of gravitational orbits, and ensemble forecasting of weather. They also play a crucial role in the dynamics of neural networks and bounded rational potential games in game theory and economics. Statistical physics provides a quantitative description of phenomena like superconductivity, superfluidity, turbulence, and collective behaviors in solids and plasma. It also explains the structural features of liquids and underpins modern astrophysics. In solid-state physics, statistical mechanics aids in studying liquid crystals, phase transitions, and critical phenomena. Many experimental studies of matter rely entirely on statistical descriptions. These include the scattering of cold neutrons, X-rays, visible light, and more. Beyond physics, statistical mechanics has significant applications in material science, nuclear physics, astrophysics, chemistry, biology, and medicine. For instance, it helps in the study of the spread of infectious diseases. Moreover, analytical and computational techniques derived from the statistical physics of disordered systems can be extended to large-scale problems. One such example is machine learning, where these techniques are used to analyze the weight space of deep neural networks. Statistical physics is also finding applications in medical diagnostics. As you can see, the principles of statistical mechanics are not confined to theoretical realms, but have profound impacts on various scientific and practical domains.